Okay, good morning, and we're going to move on today to radioactivity. So we're going to be looking at the three main forms of radioactive decay, and we're also going to be looking at how we can calculate what elements will change into by looking at the AZ notation of different elements. So the three main types of decay are alpha, beta and gamma. Now, atoms decay because they're essentially unstable. They need to give up some of their energy. So they do this by emitting either a particle or a small bit of radiation. There's actually more than three types. There's quite a few. There's neutrons and there's beta plus and other types as well. But these are the three main types, and these are the only three we need to know for GCSE. So we need to be able to describe the nature of these three different types of decays, and we also need to be able to describe how far these particles will travel under certain circumstances and how ionizing they are, which is really how dangerous they are. So we'll start off with alpha. Now, an alpha decay is essentially a helium nucleus. So we've got 2 protons and 2 neutrons. It's really important that if you're describing alpha radiation, you describe it as a helium nucleus, not a helium atom. A helium atom has electrons orbiting. That's something completely different. So essentially, we have some radioactive isotope, and it just gets a bit too excited and emits 2 protons and 2 neutrons at a high speed. Now, this is a relatively massive particle, so it contains quite a lot of mass. So alpha radiation has a short range, and it's stopped by a thin sheet of paper or a couple of centimetres of air. These are things that will stop it, but because it is such a massive particle, it's also highly ionizing. One alpha particle can ionize around 8,000 atoms, which means it can change the chemical makeup of these atoms by removing one of the outer electrons, and therefore it is quite dangerous. But it's only dangerous inside the body, because outside of the body it would have been stopped by your skin. So if you were to ingest alpha radiation, that would be really bad, but if it's just around the air, it's not too bad. But we'll look at the safety and different ionization levels on a different lesson. Right, moving on to the next type, which is beta. So in beta radiation is a high speed, or high energy, we should say, electron. So just written by a little e with a minus. Again, we'll have simply a nucleus of an atom, and it's just going to emit an electron. We'll discuss where this electron comes from in just a second, but for now it's essentially created in the nucleus and gets emitted at high speed. Now, this is moderately ionizing. Electrons have a very small mass, so they don't really ionize much at all. It just emits it. And the last one I want to look at is gamma radiation. Now, gamma radiation emits a photon, a gamma photon, which we draw with a wiggly line and this symbol here. And it's basically just a piece of electromagnetic radiation. It doesn't change the makeup of the nucleus. The nucleus has just got too much energy, so it releases it as a gamma photon. And this is weakly ionizing, so it has to score a direct hit on an atom in order to ionize it, but it's also highly penetrating, so it can travel through quite a lot of materials. So this one is dangerous outside of the body because it can easily travel through your skin. But on the other hand, it's fairly weakly ionizing, so it's not too bad. That's a brief introduction. Now, what we need to be able to do is look at the atomic notation and describe the different decays that way. So I'll go through this again and I'll show you how that is done. So So first of all, I'm going to have element X. This could be any element, it works for that. And we're going to say we've got a mass number of A, an atomic number of Z. I'm not sure how your chemistry teacher notates this, but this is how we do it in physics. So A is the mass number, which is the total number of neutrons and protons, and Z is going to be the atomic number, which is just the number of protons. I have no interest in the electrons, that's chemistry, so we're not interested in that. It's not a chemical, just neaten that up, it's not a chemical equation, it's a nuclear equation. Now this is for alpha. Now what happens is it's going to transmutate, i.e. it's going to change its element. Remember, if we change the Z number of an element, if you change the proton number, you're turning it into a different element. And because we're emitting a helium nucleus, we're losing 2 protons and 2 neutrons. So this is going to be element Y, and we're going to have the notation Z minus 2. I know my Z's and 2's look the same, but tough. And we're going to lose 2 protons, 2 neutrons, so we're losing 4 nucleons, so it's going to be A minus 4. Now, these have to balance. You can't just, get rid of them and have them disappear into thin air. So this gives an alpha particle, which I can write as He42, which is a helium nucleus. You could also write that as an alpha, but I will draw the 4 and the 2 on as well. Now, if you look at the A number here, whatever your A number here, you've taken away 4 at this point and you've added 4 at this point, so the A number remains a constant. The Z number, you've taken away 2 at this point and you've added 2 at that point, so again that remains constant, so it all balances. Alpha is quite simple in that respect. Moving on to beta decay. Now this is probably the hardest one. Where something strange happens. I'm going to use the same notation, so A, Z, element X, and this one's going to undergo a beta decay. So it's going to change into a new element Y. Now, what actually happens in beta decay is that one of these protons here, one of the neutrons turns into a proton. A proton is actually marginally more stable than a neutron, so all neutrons in the end will ultimately turn into protons. But it takes a very, very long time. But in certain elements, the conditions are right for that to happen reasonably quickly. So we're going to gain a proton, because we're turning a neutron into a proton, but we're actually going to keep the A number the same. I'm not emitting neutrons or protons, I'm simply turning a neutron into a proton. So the A number remains the same, but the Z number goes up by 1. And of course we'll have 1 fewer neutrons. Now that sounds odd because it's called radioactive decay and your proton number increases, but that's how it works. Now we've got to conserve charge in this, so in order for this to be correct, we have a certain amount of charge over here. You can't just generate an extra charge. Charge is the fundamental property, it has to be conserved. So if you gained an extra one here, we need something with a negative charge, which we're going to have a beta minus particle, which is just a high speed electron or high energy electron. And that's it for beta decay. For gamma, it's ridiculously easy. I don't actually think this is on the specification because it's so easy, because essentially nothing happens. All that happens is it goes to the same element, so the same A and Z number, plus a gamma photon. So nothing internally changes with gamma radiation, it simply emits a piece of radiation. Now I'm just going to work through a couple of worked examples for alpha and beta, and then if you can log back onto Teams and attempt the worksheet that I have set you. So we'll do an example of alpha. So I'm going to make up some elements, it doesn't matter what they are. We'll have 90 and 136 element X, whatever that is. I haven't got a periodic table to hand. And this is going to decay via alpha decay. So the rules are the proton number, this bottom one, the atomic number, goes down by 2. So that will turn into 88. Whereas the mass number goes down by 4, so 136 will go to 132. Now because this number's changed, it's a different element. It's not the same element, so we're just going to write element Y. Go and look it up on a periodic table, somewhere near gold or something. And to balance all this, we also need to have a 4-2 helium nucleus emitted, otherwise known as an alpha particle. Now in the exam, what you'll probably get is something like this, but they'll miss something out and they'll ask you to fill in the gaps. So you'll be able to identify it's an alpha decay down here and basically fill in the missing numbers. One of these numbers will be missing, so it's the process. You won't be required to learn the atomic numbers of all the periodic tables. If they do, they will give you a periodic table in the exam, so don't go away and learn all them. There's no need. We'll do one for beta. I don't know, aluminium's a good beta emitter, so we'll do that. That's 2713. I will call it X, even though that is aluminium. This is going to emit via beta decay, so the rules are the same number of neutrons and protons at the top, but this time we're going to add a proton because a neutron, remember, has turned into a proton, giving us 14 at the bottom. And that's element Y plus a beta particle. And these numbers, these charge numbers do add up. You've got 13 charge there. I know you've got 14 charge here, but you've actually got a -1 charge there, so that means that charge is still conserved. I won't go through a gamma one because the numbers just stay the same, so that is easy, and they tend not to test you on that because it is too easy. So what you need to do now is have a look at the worksheet, and there's plenty of these examples to be getting on with. Just make sure you're familiar with filling in the gaps and knowing how to do the notation for alpha and beta. Remember, beta is the hard one, that's where you have to add 1 at the bottom down here. Thank you very much.